In the last lecture, I showed this slide which shows that Earth climate is not stable. It has three solutions. The present climate, 15 degrees centigrade. 20,000 years ago, we were in the last ice age, which was 5 degrees, 7 degrees colder than present. And 600 million years ago, we had what is called snowball Earth. See, because of the change in albedo of the Earth atmosphere system, we had three possible states, and we can easily move one to the other if the system is perturbed. Okay? That is why we have to be cautious, because if we perturb the Earth's climate too much, it can move into another state. So, we also discussed how this extreme ice ages called snowball Earth occurred under a special circumstance of CO2 playing a role, incoming radiation playing a role, and the supercontinent in the tropics, which was there at that time, also played a role. Okay? So, we saw that 600 million years ago, incoming radiation was somewhat lower. Okay? Carbon dioxide was lower, and most of the continents was around the tropics, and that is what led to conditions of a snowball Earth. Right? Now, the lesson from snowball Earth is that Earth's climate can be quite unstable on account of a combination of ice albedo feedback and greenhouse effect. Okay? Now, the presence of stratosphere because of the ozone layer makes Earth's climate somewhat complex. Okay? We discussed that. We showed how increase in carbon dioxide warmed the troposphere, but cooled the stratosphere. So, this is an unusual result, which is there only on Earth, because Earth has a ozone layer, and ozone layer is essential for life to exist on land. Now, if you run a radiative transfer model and only put water vapor on Earth, you will get this distribution temperature. Okay? There will be no stratosphere. If you add carbon dioxide, it will get a little warmer because of greenhouse effect increase, and it will go along this line. Only when you add ozone that we get the stratosphere. Okay? So, Earth is unique in having a troposphere and stratosphere, and they play a different role when CO2 is increased, and that we discussed in this course. And also we discussed the fact that ozone in the stratosphere is good for us. It protects us from the ultraviolet radiation, while ozone next to the ground is bad for our lungs. So, there is a good ozone and there is a bad ozone. Now, we already discussed radiative forcing, a very important concept to understand how Earth climate can change, and we saw radiative force can occur either due to changes in solar radiation, volcanic eruption, or human induced causes. Okay? And these are all external to what is happening within the Earth, and feedback are the changes in the Earth system due to this perturbation, and these are changes that occur to change in temperature, that they increase the water vapor or changes clouds or causes more ice melting. So, all feedbacks are caused by temperature changes which cause further changes in the Earth's climate system. Okay? And radiative forcing, the concept used in IPCC initially was that the instantaneous radiative forcing caused by some perturbation in which change in temperature in stratosphere is not accounted for. Later they accounted for it, but finally they have now defined an effective radiative forcing where they account for fast adjustment of the stratosphere and the troposphere, and then look at the remaining change, because some changes occur immediately because atmosphere has got a very small mass, other changes occur slowly because the ocean is very, very massive and responds very slowly. Okay? So, you can think of forcing as external and then feedback as a response to the forcing. Now, in addition to greenhouse gases, aerosols also play a role. Aerosols are released by industrial air pollution, and we saw the impact of aerosol very complicated, because aerosol can reflect radiation, they can also absorb radiation. If they only reflect, they will cool the earth. If they absorb radiation, they will heat the atmosphere and cool the surface. In contrast to carbon dioxide, aerosols are not uniformly mixed. They have a very small lifetime and they cause an increase only locally where you are releasing the aerosol. That is a very complicated situation. Now, in IPCC, the aerosol forcing is given a large uncertainty. You can see this dotted line. We do not know whether it is 0 or can be even -3, because aerosol is complicated. There is soot, there is sulfate, organic carbon and many other emissions. Okay? While the greenhouse gases like carbon dioxide, chlorofluorocarbon, methane, they are well understood, and so their value is well known with a small variation. So, if you combine these two, we get a fairly large distribution of what is forcing the Earth's climate. So, it is not a one number, there is with a distribution. So, that is unavoidable because of the large uncertainty about aerosols. Now, aerosols also influence the clouds in many ways. Okay? We discussed that in great detail, and I will not go through it again, but just remind you that there are 4 to 5 different ways in which aerosol impact clouds. Now, clouds also are very complicated on Earth. There are high clouds like cirrus, and there are altocumulus, and there are stratocumulus, and then there are cumulus. Each cloud has a different impact on climate. Some clouds cool the Earth, some clouds warm the Earth through greenhouse effect. So, this is what still leads to uncertainty about how the climate will change in the future. Now, this can be understood that low cloud cause more reflection of solar radiation and cool the Earth. High clouds cause trapping of Earth's radiation, that is greenhouse effect, and cause warming. And so, since clouds come in many forms, the total effect of all clouds is still not fully understood. Different models give different results. Okay? And we saw that the total temperature change of the Earth is the initial temperature change, and 1 by 1 minus f, the feedback factor, which is usually positive. And if f tends to 1, we have a very large increase in climate for a small perturbation of delta T 0. So, this is what causes concern. We do not know the value of f accurately. If it is around 0.1, it is okay, we can manage. If it is around 0.9, we are in trouble, because the initial perturbation will be amplified 10 times. Okay? So, we are at the present climate around 15 degrees centigrade global temperature. We were in the ice age 20,000 years ago, around global mean around 8 degrees. Now, we are warming the Earth already by 1.5, and if we warm further, there is a risk that we will jump from this state to another state in which there will almost be no ice or snow. Okay? When will that happen? We do not know. That point is called the tipping point. If you push the Earth's temperature more and more, there comes a point where the Earth on its own will shift to a different state, which is much warmer than the present climate, maybe 4 or 5 degrees warmer, which will be totally unlivable for human beings. So, one concern we have is the so-called Atlantic meridional ocean circulation, which we discussed in some detail in this course. So, early warning signals indicate that Atlantic meridional ocean circulation or the Amazon rainforest may act as a tipping point. It may push the Earth into some other state. Okay? So, we may be approaching the tipping point, but we do not know when. It may happen 20 years from now or 100 years from now, that we do not know. Okay. The second problem we have is regarding the lifetime of greenhouse gases. We have released many kinds of greenhouse gases. Some of them, like carbon tetrafluoride and SF6, have a long lifetime of hundreds of years, and so does carbon dioxide. But others, like nitrous oxide, HFC 134a, methane, have a short lifetime. So, those greenhouse gases which have a long lifetime, we have to worry about now, because if we do not bring their emissions down immediately, they will impact over a long period. Well, gas like methane, which is there only for 10 years, its impact will be much smaller, although it is a very powerful greenhouse gas. So, one example of that is carbon dioxide. If we start reducing carbon dioxide, let us say by 2030 dramatically, okay, the concentration will not change for many years. It will take almost 50 years before concentration stabilizes, and maybe it will start coming down. So, the lifetime of greenhouse gases is a very important issue, because that determines when the concentration will stabilize after we bring down the emission. Now, that led to the concept of global warming potential, which we discussed in some depth, how we compare all the greenhouse gases with reference to carbon dioxide, which is the main gas of concern to us. Okay. Now, in this course we have discussed both proxy data, climate models and simple models. We need all the three to understand the global climate change. Proxy data is very useful to understand the past climate over the last million years, but proxy data are not always reliable, because we are not able to identify the precise time when that particular sediment was established. So, we use climate models to simulate the past climate and see how well the proxy data agree with climate models. If they agree well, we know both the proxy data and climate models are reasonably reliable. Okay. Now, we need simple models, because these complex climate models are so sophisticated that sometimes we do not fully understand what is happening in that model. So, we need a simple model to interpret the result of a complex model. Okay. Now, this is happening more and more today with the advent of machine learning and artificial intelligence, because models are doing very complex tasks, and when they give an answer, we cannot accept the answer blindly. We have to make sure we understand the answer, because if we blindly believe the results of a computer simulation, we may go wrong, because there are flaws in the climate model. Climate models are not perfect. Machine learning and AI codes are not perfect. They have problems. Okay. That is why I wanted to remember that Nobel laureate Professor Manabe, who got the Nobel Prize for developing climate models, he says the prediction of climate change without accompanying understanding of it is no better than prediction of a fortune teller. Okay. It is very important to understand. Do not believe results of climate model blindly, because climate models are very complicated and they are not 100% correct. There are situations where climate models can go wrong, okay, because many assumptions have been used to develop that model. Okay. So, remember this quote from Professor Manabe is very important in the era of machine learning and artificial intelligence, because computers do many more complex tasks than we can do, but we cannot trust them totally until we know how the results was arrived at. So, we saw all the model hierarchy from the simple 0-dimensional model for global mean temperature, then 1-dimensional model, 2-dimensional, 3-dimensional, 4-dimensional is vertical, latitude, longitude and time, and we require all this model hierarchy in order to understand the Earth's climate. Okay. Now, in these models we have to do some parameterization, that is, we have to approximately account for certain factors which we could not simulate from first principles. One example is clouds. Most of the models today cannot simulate clouds from first principles, because the model resolution is 50 by 50 kilometers, while the clouds are having a dimension of 1 kilometer. So, the model does not resolve clouds. Cloud is put in there in the model in an empirical way. So, there are problems with that. Okay. So, clouds and turbulence are two things which we have to put in empirically. Now, we also showed why, because of parameterization, we have to tune the model. When you put together a model and run it first time, you will not get the correct global mean temperature. You have to adjust various parameters to make sure you get the global mean temperature and its variability correctly. So, this is necessary because models have parameterizations. Other thing is, model also has initial condition from where we start. Okay. Because of the initial condition is not known perfectly, there is irreducible uncertainty in predicting future regional climate. Global climate is fairly reliable, but regional climate is not. Okay. For example, for trends of 20 years, the climate change signal rarely emerges from the noise of internal variability of the model. Okay. This is very important, because a lot of NGOs have put out reports claiming that they can predict how the climate will change in the next 10 years in Bangalore or other districts of India. It is not possible. Over a 10-year time scale, there is a lot of internal climate variability, and the signal of climate change will be of the same order as internal variability. So, we can only predict impact of climate change on a larger scale, hemispherical and global, not local. Okay. Second thing is, model has been designed, they tend to be very stable. They are not good for catastrophic events. When a catastrophic event occurs, you cannot ask why the model did not predict it, because models are not built for that. Those are specialized events. We will need more complex model at a high resolution to predict catastrophic events like heavy rainfall, landslides, cyclone intensity and so on. So, I also pointed out that climate models are very reliable for temperature or a large area, but not rainfall. Climate models are able to capture decadal variability, but not year-to-year variation. Climate models become more realistic only when their resolution goes below 20 kilometers. Right now they do not, but in a matter of 10 years that will happen. Models are not good for predicting local climate change. This is very important, because all the policy makers want models to predict local impact of climate change, because that is what people want. But unfortunately, we are not in a position to predict the impact of increase in carbon dioxide on local climate, like a local district or a city. Okay? We cannot. So, you must remember that the coexistence of internal climate variability makes prediction of regional climate change very uncertain. So, Clara Desser clearly states there is inherent uncertainty in regional climate projections. Okay. She is sure there is uncertainty, we cannot do anything about it. Now, we also saw that models are quite good and predict the impact of volcanic eruption. Volcanic eruption cause a cooling of the troposphere and the Earth's surface and warming of the stratosphere, and these models are able to predict very accurately. Okay. This is an example from the work of Ben Center on the eruption of El Chichon and Pinatubo. Both caused a cooling of the order of 0.5 to 1 degree, and the models were able to capture it. Okay. Now, models also showed that the temperature of the stratosphere increased during volcanic eruption, but due to increase in CO2, it is cooling. So, stratosphere is cooling over the long term, but now and then it will heat up if there is a volcanic eruption. That is brought out by models and observations. Now, we also saw that if you look at a high resolution model simulation along with proxy data, we show that carbon dioxide increased in the earth due to increase in Antarctic temperature, and a couple of 100 years later the global temperature changed. So, the work by Dr. Shakun was able to prove that it is carbon dioxide which is causing global warming, and it is not that global warming is against carbon dioxide, although it could have happened, but we are able to show that it is an increase in CO2 that caused warming 14,000 years ago. Okay. That is a natural phenomena, but we are able to show which occurred first and which occurred later. Now, one of the biggest challenges in predicting future climate change is the ocean circulation. It is a very complex phenomena going from Antarctica to the Arctic, and we showed that the models are not getting the AMOC that accurately, and that is a major uncertainty in our ability to predict whether there will be catastrophic climate change in the future. And we know that if you pass the tipping point, you will suddenly come to a place where this circulation will stop completely, and that will be catastrophic. Okay. So, this is still under debate because we do not understand when it is going to stop, but it will happen sometime, but whether it will happen 50 years from now or 200 years from now, we do not know. Now, the models are showing that this circulation in Sverdrup, that is million meters cube per second, is declining. Okay. But this is not same in all models. There are variations here. Okay. So, there is a risk of tipping point here, and that has been highlighted by Lohmann and Titwell-Sena in a paper published 3 years ago, and they say it depends on how fast the rate of change of climate is. If the rate is coming very fast, the tipping will occur earlier. Okay. So, that is a big worry for all of us. And Stephen Ramstorff, an expert on AMOC, has said on the basis of whole series of new studies, the risk already appears to be significantly greater in this century than what scientists had assumed some time ago. Okay. This is the warning. Okay. Now, to prevent this from happening, you have to rapidly reduce the CO2 emission from the present value around 60 gigatons to around 18 gigatons by 2040. This is a part of the Paris Agreement, but it is not happening right now. We are not able to convince all the countries to reduce CO2 emissions. Okay. Now, the budget we have is only 1,000 billion tons of carbon. If we emit beyond that, temperature will go about 2.5 degrees centigrade and can lead to catastrophic climate change. Okay. Here is an example. We are right now around 420 ppm, and the chances are that over the next 100 years temperature may reach beyond 2.5, but we allow the CO2 to go to 450, which is going to happen. It may even go to 3.5. If you are careless, go to 550, it can go to 4.5. If you don't do anything, it will go to 650, it will go to almost 5. So, this shows clearly how serious the issue is, how we need to take immediate action. Now, in the IPCC report on global warming about the 1.5 degree tipping point, there is a clear warning. Every bit of warming matters. Every year we don't take action matters, and every choice matters. This is what I want you to remember from this course. If you understood the science of climate change, you will understand that every bit of warming is bad. Every year we delay reduction of CO2 emission is bad, and every choice that every human being makes will affect our future. So, this is a warning given clearly by IPCC. Okay. And why? Because if we don't do that, as the global warming occurs, more CO2 will emerge from permafrost. Permafrost is frozen soil we mentioned earlier in the course, in which there is methane trapped in it. As the global warming occurs, all the permafrost will melt, and CO2 will come out and will accelerate global warming. Okay. Now, the myth that it will be too expensive to mitigate climate change is wrong. It will be too expensive not to mitigate climate change. That is the message you must get from this course. And Saintfield and Pandis point out in their book that if today we stop CO2 emission, the CO2 in the earth will not reach the pre-industrial value for the next 1,000 years. That is how much change we have already made. Okay. And this cartoon illustrates the status we are in. We are in this earth, which is the boat, and we are concerned only about economic growth, and we are going to reach a tipping point. This is a waterfall. Okay. And this young person is complaining, and the older politicians are not able to understand the threat, and they think that this waterfall is very far away. It may not be. Okay. So, another problem is, as we decrease the aerosol due to air pollution concern, global warming may occur earlier. That is another threat we face. And there is a risk of heat waves, wildfires and droughts, and the insurance companies which insure against this are getting concerned. Okay. And I will end by a very interesting paper that appeared in September 2024, in which they have reconstructed Earth's mean climate over the last 485 million years. Please read that. It is a very interesting account of how we are able to combine model and proxy data. With this example of how we have combined climate models and proxy data to understand Earth's climate over the last 485 million years, I conclude this course, and I hope you will benefit by understanding the science of climate change. Thank you.